In the last lecture, we introduced the idea of hypothesis testing. And in all the examples we talked about, we took a sample, and from that sample, we wanted to know whether there was enough evidence to conclude that either the mean or proportion is less than, greater than, or not equals to a single number. Those are all examples of hypothesis tests involving one sample. Today, we'll talk about situations that will involve two samples. And this situation shows up a lot in real life. Say you're a drug company trying to decide whether a medicine works. What will typically happen is you'll take one group of people, give them a medicine. You'll take another group of people, give them a placebo, which is a fake medicine, and then you're going to measure something. Now, the measurements will probably be different. And the question is, could this difference be due to regular randomness of the two groups? Or is this difference big enough for you to conclude that the medicine actually worked? So today we'll talk about hypothesis tests involving two samples. The first page here are formulas that I'll need today. And these are formulas for finding the test statistic, which is usually part C of the process. The first two formulas are formulas that we used last time, which were for the one sample situation. The first one with the Z, that's going to be for one proportions. The second one with the T, that's going to be for one mean. The next two formulas are the two formulas that are new for today. The first one with the Z and P1 hat, P2 hat, that's going to be for two proportions. The last one here with the T and X1 bar, X2 bar, that's going to be for the two means situation. And then the box at the bottom, same box as last time. These are the commands in R that we'll need. The first row, P norm, Q norm, that's going to be for Z's. And remember, Z is going to go with proportions, so both the one proportion and also the two proportions situation. The second row, PT, QT, that's going to be for T's. And T's are going to be for means. Okay, second page. Second page is talking about types of error. So I'm not going to talk about this right now, but we'll come back to this when we actually need it. Example 1. A drug company develops a new medicine. To test their medicine, a sample of 2,529 people are divided into two groups, a control group and a treatment group. The 1,304 people in the control group were given a placebo, and the 1,225 people in the treatment group were given the medicine. 150 people in the control group got sick, and 113 people in the treatment group got sick. Can the company conclude that the proportion who got sick differs between the control group and the treatment group? Use the alpha equals 0.07 level of significance. Notice that we have two groups here. We have a control group and a treatment group. So this means that we have two samples. So this will either be a two proportions or a two means situation. And just like last time, if you see the words mean and standard deviation in the question, it's going to be a mean situation. If you don't see those words at all, if you don't see the words mean or standard deviation at all in the description, it will be a proportion. So looking back at the description here, I didn't see the words mean or standard deviation at all. This will be proportions. And because we're talking about two groups, two samples, this will be two proportions. And just to remind myself, proportions will involve Z's. Part A, state the null and alternative hypotheses. So these are my H0, H1. And just like in the last lecture, proportions will involve the symbol P, means will involve the mu symbol, which is the symbol for means. So we're talking about proportions here, so we should be using P's. And because we're talking about two proportions, we're going to have a P1 and a P2. So H1 will involve a P1 and a P2. Symbol in the middle will either be a less than, a greater than, or a not equals. If we look back at our question here, it says, can the company conclude that proportion who got sick differs? So keyword differs is telling me that this is a not equals. And then because we have two samples, I recommend we label what our ones means and what our twos means. So my two groups are the control group and the treatment group. So let me say my one is the control and my twos are the treatment. So my ones are the control, my twos are the treatment. So this will help us keep things straight when we actually use the formula in part C. H0 should be the same as H1 except with an equals in the middle. H0 will be P1 equals P2. Part B, find a critical value and sketch the rejection region. Okay, so we're going to be drawing the picture, either the Z distribution or the T distribution. The picture will either be shaded to the left, shaded to the right, or two tails. If it's a less than here, it will be to the left. If it's a greater than, it will be to the right. Not equals will be two tails. Okay, and in part B, the shaded area is our alpha. Our alpha here is 0.07. Okay, so the left and right together is 0.07. And our job here is to either find Z stars or T stars. Because we're talking about proportions, we're looking for Z stars. Okay, so this is really a area to Z question. And for an area to Z question, we're talking about Z's here. It will either be P norm, Q norm. Part B is an area to Z. Area to Z, we'll be doing Q norm left area. If this were a mean question, these would be T stars and you will be doing QT here. Or no, yeah, QT here. Okay, so what is the left area for me to plug into R? It's not 0.07, so 0.07 is the left and right together. If I just want the left, divided by 2. So we'll divide by 2 to get just the left side. Okay, so on our calculator, 0.07 divided by 2. 0.035. Okay, that's just the left shaded area, which is what I want to plug into R. So we're going to be plugging into R Q norm 0.035. Negative 1.812, so round to 3 decimal places. So for two tails, I do expect two Z's. So negative 1.812 is the one on the left. The one on the right is going to be the positive version. And these are Z's. Now on your lab, you're going to enter this as negative 1.812, comma 1.812. So part B is the same as the last lecture. Part C, find the Z or T test statistic. We're talking about proportions. We should be looking for Z. And this refers to the formulas on the front page. So we're talking about Z's, two proportions. The formula for two proportions is this one. It has a P1 hat and P2 hat, P hat, no numbers, and 1 and 2. So let me write all of that down. There's a P1 hat, there's a P2 hat, there's a P hat, no numbers, there's an N1 and an N2. Okay, what are all these? P1 hat is the proportion from our sample, and in particular, the sample that goes with 1. So proportion from the control sample. So the control sample, how many people total? It's not 2529, so 2529 is the total number of people of both groups together. That's not what I want. 1 through 04 people in the control group. That's what I want. So 1 through 04 is the total number of people in the control group. And then we're talking about how many people got sick. So how many people got sick in the control group? 150 people in the control group got sick. So P1 hat is the proportion of the control group that got sick. That's going to be 150 out of 1304. So 150 out of 1304. Okay, let me enter this into a calculator. 150 over 1304, round to 3 decimal places, 0.115. P2 hat is the proportion from the treatment sample. So how many people total in the treatment group? 1,225 people in the treatment group. And then how many people got sick in the treatment group? 113 people in the treatment group got sick. So P2 hat, that's the proportion of the treatment group that got sick. That's going to be 113 out of 1225. So 113 out of 1225. Okay, so on a calculator, 113 out of 1225. Round to 3 decimal places, this is 0.092. P hat, no numbers. What is P hat, no numbers? If we look back at the formula sheet, it says P hat, no number, is the pooled proportion P hat equals x1 plus x2 on top, n1 plus n2 on the bottom. So P hat, no numbers, means just combine those two groups together. So combine P1, P2 together. So on top, how many people total got sick? So that's going to be 150 from the control group plus 113 from the treatment group. On the bottom, N1 plus N2, so how many people total from the two groups? That's going to be 1304 from the control group plus 1225 from the treatment group. So basically, P hat, no numbers, you're going to take the numerators of P1, P2 hat for the top, add them together. For the bottom, take the denominator from P1 hat, P2 hat, and add them together. All right, so on the calculator, I'm going to enter it just like that. So fraction up top, 150 plus 113. On the bottom, 1304 plus 1225. Okay, round to 3 decimal places. This is 0.104. N1, N2, these are my sample sizes. N1, how many people total for the control group? That should be the bottom of P1 hat, so 1304. N2, how many people total in the treatment group? That should be the bottom of P2 hat, so 1225. Okay, so we have P1 hat, P2 hat, P hat, N1, N2, so enter all of that into the formula. All right, so I'm going to start off with a fraction. Up top will be P1 hat minus P2 hat. So P1 hat is 0.115 minus P2 hat is 0.092. On the bottom, big square root. So square root P hat 1 minus P hat. So P hat, no numbers, is 0.104. So 0.104, parentheses, 1 minus 0.104. Now, for the bottom here, inside the square root, when you enter it, don't enter any spaces, right? Because we want everything to be inside that square root. So you put spaces there, what will probably happen is part of your formula will be outside of that square root, which you don't want. You want everything inside the square root. So don't enter spaces. Okay, and then next will be parentheses, fraction, 1 over N1, our N1 is 1304. Okay, plus, so I'm going to move my cursor just to the right of the fraction without putting a space, plus another fraction. This one will be 1 over n2, 1 over 1225. Okay, close parentheses. Okay, make sure what you see on decimals looks exactly like this formula. In particular, for the bottom, make sure everything is inside that square root. And then we'll hit enter. So I'm getting 1.894. That's rounded to 3 decimal places. And this is my z. Part D. So part D will be the same as what we did in the last lecture. Find a p-value. We're going to start off by drawing our picture. Should be the same picture as in part B. Should still be 2 tails because of the not equals. And then on the picture, we're going to put the test statistic that we found in part C. So 1.894. Because this is 2 tails, there should be two z's. The positive 1.894 is the one on the right. The one on the left is going to be the negative version. And our job here is to find the p-value. So p here stands for probability. Probability is another word for area. So we're looking for the area of these two shaded regions together. This is a z to area question. So for z's, it will be p norm or q norm. This is a z to area, p norm. So p norm I have two z's here. I have negative 1.894 and a positive 1.894. Which one do I enter here? So the way p norm works is you feed it a z and it will give you the area to the left of that z. So I don't want to plug in the positive version because the area to the left includes this unshaded part that I don't want. Okay, so I'm always going to enter the negative version. So for the 2 tails, I'm always going to enter the negative version of the z because to the left of the negative version is just the shaded area that I want. So negative 1.894. Okay, we'll do p norm. Negative 1.894. Round to 3 decimal places. This is 0.029. P norm always spits out the left area. So this 0.029 is the left area. So the area to the left of negative 1.894, which is this part here. I want both regions together. The one on the left is 0.029. By symmetry, the one on the right is also 0.029. So together, you can either take both of these and add them together, or take one of them and just multiply by 2. So I'll multiply by 2. Our p-value is going to be 2 times 0.029. So on a calculator, 2 times 0.029. 0.058. That is our p-value. Okay, this was for a proportion situation. If this were a mean question, these will be t's, and then you'll be doing pt here. Part E, reject or don't reject. So the way you decide is look at your p-value and look at your alpha and check if it's less than or not. So we're going to look at our p-value and see if it's less than our alpha. Our p-value is 0.058. Our alpha, 0.07. And the question is the p-value less than the alpha? And my recommendation here is add on 0 so that they both have the same number of decimal places, because that's going to help you compare. 0.58, that's 3 decimal places. 0.7, that's only 2. I'm going to add on this 0. And we're basically comparing 0.58 versus 0.70, which is basically 58 versus 70. So is the p-value less than the alpha? Yes, right? 58 is less than 70. Okay, if it's a yes, you reject. If it's not less, you don't reject. So because it is less here, we're going to reject. And then for our conclusion, so this sentence is basically saying, can you conclude that H1 is true? State your significance level. At alpha equals 0.07 in this case. Level of significance, there is or is not. So if you reject H0, then there is enough evidence to say that H1 is true. If you did not reject H0, then there is not. So because we did reject, there is enough evidence to conclude that, and then you're basically going to write H1 as a sentence. And usually I get this from the question. So can the company conclude that the proportion who got sick differs between the control group and the treatment group? So I'll just write that part. There is enough evidence to conclude that the proportion who got sick differs between the control group and the treatment group. Part G. So part G is a new part in this lecture. What type of error could have occurred? What is the probability of this error occurring? So this, I need to talk about the second page in the lecture notes. Because we are making our decision to reject or don't reject H0 from a small sample, instead of getting data from everybody in the population, there's always the possibility that we are really unlucky and that we got a sample that told us to do the wrong thing. So every time you're doing a hypothesis test, you could end up with either a type 1 error or a type 2 error. And the type of error depends on whether you ended up rejecting H0 or don't reject H0. So every time you reject H0, you could be making a type 1 error. Every time you don't reject H0, you could be making a type 2 error. So in our example 1, we ended up rejecting H0. So every time we reject H0, we could have made a type 1 error. Okay, so to answer our question, what type of error could have occurred? Could be a type 1 error, right? Because we ended up rejecting H0. So this is an error where the sample told us to reject H0 when in fact H0 was actually true, which means we should not have rejected. So why is this rejection occurring? So if H0 was indeed true, then most of the time our sample should end up in the unshaded part. But we were just unlucky in this case and ended up with a sample in the shaded part, which told us to reject. So what is the probability that we just land in the shaded part by just regular randomness? Well, the area of the shaded part here is exactly alpha. So that's the probability that we land in the shaded part by just regular randomness. So the probability of making a type 1 error is actually just the alpha. Okay? So to answer our question here, what is the probability of this error occurring? For a type 1 error, it's just alpha. And then I didn't ask it here, but I will ask it in the lab, how do you reduce the error? So because the probability of type 1 error is alpha, to reduce it, just lower the alpha. One small correction. So the probability of a type 1 error is alpha. And because we actually know what the alpha is, I want you to state it. So probability of a type 1 error is alpha, and our alpha in this particular example was 0.07. Okay, so the full correct answer to part G is the type of error that could have occurred is type 1. The probability of it occurring is 0.07. Example 2. A simple random sample of 17 business majors from a certain university had a mean GPA of 2.81 with a sample standard deviation of 0.27. A simple random sample of 23 psychology majors was selected from the same university, and their mean GPA was 2.97 with a sample standard deviation of 0.23. Can you conclude that the mean GPA of psychology majors is greater than that of business majors? Use the alpha equals 0.02 level. Notice that we're talking about two groups here. We're talking about the business majors and the psychology majors. So this will be two something, either two proportions or two means. If you see the words mean and standard deviation in the question, which we do here, mean, standard deviation, it will be a mean situation. So this would definitely be a two means question. If you don't see those words, if you don't see the words mean or standard deviation at all, it will be a proportion situation. For means, we should be using t's. Part A, state the null and alternative hypotheses. This is our H0, H1. Because we're talking about means, I should be using the symbol for mean, which is mu. And because we're talking about two means, I should have a mu1 and a mu2. And the question is, what sign goes in the middle? Less than, greater than, or not equals. So if I go back and read my question, can you conclude that the mean GPA of psychology majors is greater than? So greater than is telling me that I should have a greater than symbol. And then as always, I recommend you label what the ones mean and what the two means. So my question is, can we conclude that psychology majors is greater than business majors? So the ones would have to be psychology. And the twos will be my business. Okay, psychology greater than business. Psychology majors is greater than that of business majors. H0 should be the same as my H1, except with an equals in the middle. So my H0 will be mu1 equals mu2. If this were a proportion question, these would be P1, P2. Part B, find a critical value and sketch the rejection region. So we'll draw the picture, either the Z distribution or the T distribution. And this picture should either be shaded left, shaded right, or two tails. If this is less than, it will be shaded left. Greater than, like it is here, will be shaded right. And not equals will be two tails. The shaded region is our alpha. Our alpha here is 0.02. So 0.02 is the shaded region, which is the area to the right here. And we should either be looking for a T star or a Z star. We're talking about means, I should be looking for a T star. So this is really an area to T question. So in R, for the T situation, area to T, we should be doing QT, left area DF. QT, left area DF. What is the left area here? Is it 0.02? No. So 0.02 is the shaded area, which is the area to the right. What I want is the area on the left side, which is this unshaded part. So to get the other side, I need to do 1 minus. So 1 minus 0.02. So on my calculator, 0.98. So 0.98 is the area on the left side here. And that's what I need to feed into QT. So QT, 0.98. Now QT also has a degrees of freedom. And from our last lecture, degrees of freedom is 1 less than the sample size. But what do you do when you have two samples? So you don't combine them. So if you have two samples, you're going to take the smaller sample size and use that for your DF. So my sample sizes are 17 business majors and 23 psychology majors. So the smaller sample size will be 17, and then degrees of freedom will be 1 less than that. So 1 less than 17 would be 16. So once again, this is the new part in this lecture. If you have two samples, pick the lower sample size, which in this case is 17, and then degrees of freedom will be 1 less than that sample size. So 1 less than 17 would be 16. Okay, in R, Qt 0.98 comma 16. Okay, round to 3 decimal places. This is 2.235. Okay, this is my T star. Now, for picture shaded to the right, we do expect our critical value and our T in the next step to be positive. So if you're not getting a positive answer here, what probably happened was you forgot to do the 1 minus there. Part C, find a Z or T test statistic. We're talking about means, so I should be looking for a T. And then if we look at our formula for two means, our formula for two means has a x1 bar, x2 bar, s1, s2, n1, n2. So let me write all that down. Okay, so I need to find an x1 bar, an x2 bar, an s1, s2, an n1, and an n2. Okay, what are these things? Okay, x1 bar is the mean from the sample, the first sample. So my ones were psychology, so x1 bar should be the mean for psychology. What is the mean for psychology? So it's not 2.81. 2.81 was the mean for business, but my 1 is psychology. So what is the mean for psychology? Psychology majors, their mean was 2.97. So x1 is 2.97. x2 bar, that should be my mean for the business, which is the 2s. Mean for business is this 2.81. S1, so S's stand for standard deviation. So S1 is the standard deviation for my 1s, which is the psychology. Standard deviation for psychology. So psychology was talked about in the second sentence. Sample standard deviation 0.23. So 0.23, psychology standard deviation. S2, that should be the standard deviation for the business, my 2s. Business was this first sentence, standard deviation 0.27 for the business majors. 0.27. N1, sample size for my 1s, so sample size for psychology. Psychology, how many people? Simple random sample of 23 psychology majors, so 23 for my N1. And then N2, sample size for my 2s, which is the business. Business sample size. Random sample of 17 business majors, so 17 is my N2. Okay, plug everything into the formula for T, for two means. So two means would be this one. So on my calculator, I'll start off with a fraction. Up top, x1 bar minus x2 bar, that would be 2.97 minus 2.81. Okay, on the bottom, big square root. So square root, fraction. So that first fraction is s1 squared over n1. So s1, 0.23, squared, don't forget the square. And on the bottom, n1 is 23. Okay, move the cursor just to the right of the fraction, don't put a space, plus another fraction. Okay, make sure that everything is inside the square root. So don't put any spaces when you enter this. Second fraction, s2 squared. S2 is 0.27 squared over N2. N2 is 17. Okay, make sure what you see on Desmos looks exactly like the formula here. In particular, make sure that these two fractions on the bottom here are inside that square root. And then hit enter. So I get 1.971. Okay, this is a t. 1.971. Okay, so like I said, for pictures that are shaded to the right, we expect the critical value and our test statistic to be positive. So if you got a negative here, what probably happened was you swapped your 1s and 2s. Okay, that's why I said to label your 1s and 2s so that you have it in the right order. Part D, find a p-value. So draw the same picture. Okay, this is greater than, so it should be shaded to the right. So same picture as in part B. Put your test statistic that you found in part C on a picture. That goes down here, 1.971. And your job here is to find that area. So this is a t to area question. So t to area is going to be pt, t, comma, df. So we're going to do pt. The t, which is 1.971, comma, df. So df, degrees of freedom. So just like in part B, if we have two samples, you're going to use the smaller sample size. So our smaller sample size, our sample sizes are 23 and 17. Smaller sample size will be the 17, and then degrees of freedom for 17 will be 1 less, 16. Okay, so PT in R, 1.971, comma 16. 0.967. So round to 3 decimal places here, 0.967. Okay, p-values should be pretty small numbers. 0.967, that's a big number. So we're not done yet here. Because the way PT works and p-norm, you plug in z's or you plug in t, df, it spits out a left area. Are we looking for a left area here? No, right? We're looking for this shaded area on the right side. So 0.967 is the left side, which is this unshaded part. To get the other side, we have to do a 1 minus. So our final answer is going to be 1 minus 0.967. .033. So once again, p-values, we do expect small numbers. So if you end up with a big number, either you forgot to do a 1 minus or you did a 1 minus when you shouldn't have. Part E, reject or don't reject. So to decide, we're going to look at our p-value and see if it's less than the alpha. Our p-value is 0.033. Our alpha, 0.02. Okay, question is the p-value less than the alpha? And to help me compare, I usually add on zeros so they both have the same number of decimal places. 0.33 has 3 decimal places. 0.2 only has 2. I'm going to add on the 0 here. So this is really 0.33 versus 0.20. So 33 versus 20. Is 33 less than 20? No. So if it's a no, you don't reject. And part F, our conclusion. So this sentence is really asking, can we conclude that H1 is true? So state your significance level at alpha equals, this question is 0.02. Level of significance, there is or is not. So if you did not reject H0, there is not enough evidence. to say that H1 is true. So then there's not enough evidence to conclude that, and we'll just translate H1, which I usually get from the original question. Can you conclude that the mean GPA of psychology majors is greater than that of business majors? So that part. There is not enough evidence to conclude that the mean GPA of psychology majors is greater than that of business majors. Part G, what type of error could have occurred? And what is the probability of this error occurring? Okay, so back to my second page about the errors. So if you rejected H0, then you could have a type 1 error. If you did not reject H0, you could have a type 2 error. In this case, we did not reject H0, so don't reject H0 goes with type 2. So we could have a type 2 error. Okay, and the second question is, what is the probability of this error? So probability. So go back to the second page here. So type 2 error occurs when we don't reject H0 when in fact H0 was false. Probability of type 2 error is beta. So we're not going to actually compute beta here. So if you have a type 2 error, the probability, you're just going to write beta. So there is a way to compute beta, but that's a little bit too advanced for this class. So if you take a more advanced stat class after this class, you will probably see a way of computing beta. I didn't ask it here, but in your lab, I do ask you, how do you reduce the probability of a type 2 error? So to reduce the probability of a type 2 error, you would increase the sample size. Why is that? Well, in this case, we ended up with a don't reject because we just got unlucky and got a test statistic that was not in the shaded part. Right? This test statistic is in the unshaded part, which led to a p-value that was too big. Right? It wasn't smaller than our alpha, which led to us not rejecting. So one way to reduce the probability of that happening is to increase the sample size. So mathematically, why does that work? So right now, our test statistic was in the unshaded part. So if I increase the sample size, let me go back to the formulas. If I increase the sample size, what happens? So sample sizes are N1, N2 here. Okay, so just focus on the bottom. If I increase the sample size, right, that would be increasing the denominators. That would make each of these fractions smaller, right, which would make the whole thing on the bottom smaller. And so if you're dividing by a smaller number, overall, you should get a bigger number. So currently, our test statistic was in the unshaded part. So if you increase your sample size, that should make your test statistic larger. And if you make it larger, there's a better chance that you're going to end up in the shaded part, which will lead to a reject. Okay, so point of the story is, so if you don't reject, you could have a type 2 error. The probability of a type 2 error is beta, and to reduce the probability of a type 2 error, you increase the sample size. Example 3. The concentration of benzene was measured in 5 random specimens of untreated wastewater produced at a gas field. The mean was 7.8 milligrams per liter with a sample standard deviation of 1.4 milligrams per liter. 7 random specimens of treated wastewater had a mean benzene concentration of 3.2 milligrams per liter with a standard deviation of 1.7 milligrams per liter. It is reasonable to assume that both samples come from populations that are approximately normal. Can you conclude that the mean benzene concentration is less in treated water than in untreated water? use the alpha equals 0.03 level. So notice that I am talking about two groups here. I'm talking about 7 or 5 specimens of untreated water and 7 specimens of treated water. So 2 groups, 2 samples. This will either be 2 means or 2 proportions. So if you see the words mean and standard deviation in the question, it's going to be a mean situation. If you don't see the words mean or standard deviation at all, it will be proportions. So here I do see the word mean and standard deviation. So this would definitely be 2 means. And for means, I should be using t's. And then just as an aside here, so the reason why I had to include this sentence here, it is reasonable to assume that both samples come from populations that are approximately normal, is because the sample sizes here are really small. So 5 untreated and 7 treated. So the central limit theorem does not apply in this case because of those small sample sizes. So I do have to mention that these samples come from a normal distribution. Part A, state the null and alternative hypotheses. This is my H0, H1. And because I'm talking about means, I should be using the mean symbol, which is mu. And because I'm talking about 2 means, I should have a mu1 and a mu2. And the question is, what symbol goes in the middle? So we go back to the question here. Can you conclude that the mean benzene concentration is less in treated water than in untreated water? So I will have a less than here. And then I should always label what the 1's mean and the 2 means. So the question is, can you conclude that the mean benzene concentration is less in treated water than in untreated water? So we're trying to conclude here that the treated water is less than the untreated water. So the 1's would have to be the treated, and the 2's would have to be the untreated. So treated less than untreated. Less than treated water than untreated. H0 will be the same as H1 except with an equals in the middle. Part B, find a critical value and sketch the rejection region. So draw my picture. Either shaded left, shaded right, or 2 tails. This is the less than. This is going to be shaded left. If this were greater than, it will be shaded to the right. If it's not equal, it will be 2 tails. The shaded area is our alpha. Our alpha here is 0.03. Okay, that's the shaded area, which in this picture is the left side. And your job is either to find the Z star or the T star. Because we're talking about T's here, this should be a T star. Okay, this is an area to T question. So area to T, T's, area to T, QT left area DF. So QT left area DF. So what is the left area here? Is it 0.03? Yeah, it is here. So 0.03 is the shaded area, which in this particular case is the left side, so I don't have to do anything to it. So the left area is 0.03. QT has a DF, so comma, degrees of freedom. And remember, when we're talking about 2 samples, we use a smaller sample size. So our sample sizes are 5 untreated and 7 treated. So the smaller sample size will be the 5, and degrees of freedom will be 1 less than the sample size. So 1 less than 5 would be 4. Okay, so in R, we're going to do QT, 0.03 comma 4. Rounded to 3 decimal places, this is negative 2.601. Okay, this is a T star. Okay, so for picture shade to the left, I do expect the critical value to be negative. So if for some reason you did not get a negative, what probably happened was you did a 1 minus when you shouldn't have. Part C. Find a z or t test statistic. We're talking about t's here, so I should be using the t formula for two means. So the two means formula has an x1 bar, x2 bar, s1, s2, n1, n2. So let me write all that down. So x1 bar, x2 bar, s1, s2, n1, and n2. Okay, the bars, those are the means. So x1 bar is the mean for my ones, which is the treated. So mean for treated. So where am I talking about treated? Not the first sentence. First sentence is untreated, which means these means are untreated. 7 specimens are treated, had a mean of 3.2. So x1 bar, the mean for treated is 3.2. x2 bar is the mean for untreated. Untreated was this first part. The mean was 7.8. S1, so S's are standard deviation. So standard deviation for my ones, so standard deviation for treated. Treated was the middle part here, so standard deviation 1.7. S2, standard deviation for my twos, which is the untreated. Standard deviation for the untreated. So untreated was the first part here. So untreated was standard deviation 1.4. N1, sample size for my ones, sample size for the treated, sample size for the treated, 7 random samples, random specimens of treated. So N1 is 7. N2 should be the sample size for untreated, 5 random specimens of untreated. So 5 for the untreated, which are my twos. Okay, so that's why I said to label your ones and twos so that you have the right numbers for ones and twos here. Okay, plug into the formula. Okay, so this formula. So on a calculator, fraction up top, x1 bar minus x2 bar. That's going to be 3.2 minus 7.8. On the bottom, big square root. So square root, fraction. First fraction, s1 squared over n1. So s1 is 1.7 squared over n1. N1 is 7. Okay, move your cursor just to the right of the fraction. Don't put a space. Plus another fraction. And then for my second fraction, s2 squared over n2. S2 is 1.4 squared over n2, which is 5. Okay, make sure what you see on decimals looks exactly like this formula. So in particular, make sure the two fractions on the bottom are inside the square root. Okay, if they're not inside the square root, what probably happened is you added a space somewhere. So don't enter spaces when you enter the bottom. Right, so I get a negative 5.127, and that's it's a t. Negative 5.127. Okay, so for pictures that are shaded left, I do expect the critical value and the test statistic to be negative. So if for some reason you ended up with a positive answer here for the test statistic, what probably happened was you swapped your ones and twos. Right? You didn't listen to my recommendation of labeling and you accidentally swapped the ones and twos. Part D, find a p-value. So draw the same picture. Because it's less than, this will be shaded left. And then put your test statistic that you found in part C on the picture. That will be this negative 5.127. And your job here is to find that shaded area. So this is a T to area question. For T's, T to area, PT, T, DF. So we're going to do PT, the T, so that's negative 5.127, comma, the degrees of freedom. So degrees of freedom, when you have two sample sizes, you don't combine them, you use the smaller sample size. So our sample sizes were 7 and 5. Smaller sample size would be 5. Degrees of freedom would mean 1 less than the sample size, so 1 less than 5 is a 4. Okay, so in our PT, negative 5.127, comma 4. 0.003. So round it to 3 decimal places, that would be 0.003. Okay, is that my answer, or do I have to do something to it? So PT, P norm, will spit out the left area. If you're looking for a left area, you're done. If you're not, you have to do something else to it. So are we looking for the left area here? We're looking for this shaded part, right, which is the area on the left. So we are looking for a left area, which means this is going to be our answer. Part E, reject or don't reject. So to decide, look at your p-value and see if it's less than the alpha. Our p-value is 0.003. Our alpha, 0.03. Okay, and as always, my recommendation is to add on 0 so that they both have the same number of decimal places. 003 has 3 decimal places. 03 currently only has 2. So I'm going to add on a 0. And really, you're comparing 003 versus 030. So basically, 3 versus 30. Is the p-value less than alpha? Is 3 less than 30? Yes. So if it's a yes, we reject H0. So here we reject. Okay, if it's not less, you don't reject. Part F, so this is our conclusion. So the sentence is saying that, do we have enough evidence to conclude that H1 is true? So at, state your level of significance. So at alpha equals, it was 0.03 here. Level of significance, there is or is not. So if you reject, then there is enough evidence to say that H1 is true. If you did not reject, there is not enough evidence. So there is enough evidence to conclude that, and then whatever H1 is saying. And usually I just copy the sentence from the question. Can you conclude that the mean benzene concentration is less in treated water than in untreated water? So because we did reject H0, we can say that H1 is true. And H1 is saying that the mean benzene concentration is less in treated water than in untreated water. Okay, part G, what type of error could have occurred and what is the probability of this error? Okay, so we rejected H0. So anytime you reject, you could have a type 1 error. Okay, so type 1. Second part of the question, What is the probability of this error? So for a type 1 error, the probability is alpha. And actually, in this case, we know what alpha is. So alpha was 0.03. And then in your lab, I asked one additional question: how would you reduce the probability of a type 1 error? So for a type 1 error, the probability is alpha. So to reduce it, you lower the alpha. So lower the alpha. All right, so that is it for today. Have a great day. See you guys next time.